Thank you, Vicky. Can you hear me back there? It's on. The mic is on. Good. Okay. Thank you. It is a pleasure. I must apologize for Dr. Kaliaros. He got pulled into an important board meeting that he had to be at, and you can imagine how that sometimes goes. So he's entrusted me to talk about a similar topic. I'll be a little bit more focused because of the activities that I actually lead at the College of Nanoscale Science and Engineering. So just to get you guys started, I'll give you an outline. I could go on for a long period of time about talking about just the College of Nanoscale Science and Engineering, but what I'll do is I'll try to keep it as short as possible, then go into some nanotechnology applications, how it actually impacts clean energy, and some of the work that we are doing at the Nano College related to solar, both from a technology perspective, deployment and implementation perspective. I'll mention a few things on workforce that we actually do. And then we also host at the college the US Photovoltaic Manufacturing Consortium, which is a major DOE-funded initiative, and I'll talk a little bit about that and then try to summarize. Before I get started about the college, a couple of quick questions. How many of you over here have actually heard about the College of Nanoscale Science and Engineering? Quite a few of you. How many of you have actually visited and had a tour of the place? Not many. Okay, that's good. How many of you are local, that are from the local region? Okay, so there's a few from the local region too. Okay. All right, so this is, I'm going to try to take you, there's no substitute for actually going and visiting the college. If we host a conference here next time, I would absolutely invite you to come and at least have a tour of the place. We should maybe set aside some time to actually show you what's actually going on over there. So to begin with, the college is brand new. We consider ourselves trailblazers. We're not a typical academic institution, and you'll see that in my presentation, the thread that we have here in terms of how we do business, how we educate, the higher education that we actually provide to our students is very different. First of all, you can just see it right here. We have 4 constellations: nanoscience, nanoengineering, nano bioscience, and nanoeconomics. Weird names. Why these names? You go to a typical engineering school, you have electrical engineering, mechanical engineering, chemical engineering, and guess what? The mechanical engineers don't talk to the electrical engineers. The chemical engineers don't talk to the other ones. What we have done is shaken it all up within our different constellations. So if you look at the science constellation and you look at the faculty that are part of that constellation, we'll have a physicist there. We'll also have an electrical engineer in the science constellation. We might have somebody that has a math type background that's in the science or in the engineering constellation, or also in the economics constellation as well. So we've actually mixed it all up in a way so that we get rid of the silos. And that's how you actually generate additional opportunities. Another key feature of our college is our student to faculty ratio. We have currently about 250 students, about 60 faculty, somewhere between 60 to 65 faculty. This is a slightly older slide. Close to a 1:4, 1:5 ratio. You're not going to find that in any educational system anywhere, I mean, other than a really private prep school for that matter, and we're a public institution. Most of our faculty that we've brought on board, and the college is fairly new, it started only in 2004, we're offering degrees, the nano science and nano engineering degrees for the first time, bachelor's, master's, and PhD. The faculty that we have on board are faculty that have come from industry. And what that does is it really imparts to the students the real need that industry has for these kind of students. So that's why our students get picked up. I'll talk a little bit more about that as we go forward, but our focus is very applied technology development, manufacturing scale-up related issues, etc. So we're very closely aligned with industry. This is a sort of a picture of our facility, and the entire facility has actually just been built in the last 12 to 15 years. Okay, it's brand new. It's all state-of-the-art kind of capabilities. We have close to 800,000 square feet of space, all built in, as I said, the last 12 to 15 years. We have 85,000 square feet of what we call Class 10 clean room, which includes technology and equipment and manufacturing capability for what we call 300 millimeter semiconductor type wafers. And that's another thing that we usually are proud to talk about. Our marketing communications guys usually say that if you add up all of the Class 10 clean rooms that have 300 millimeter equipment capability in all the universities across the entire US, as well as in the world, you add it all up, that number will be 0. Okay? And we have 85,000 square feet of that kind of capability, which has become a huge magnet for industry. And I'll talk about that also in a second. And we're expanding. There's a brand new building on the top of the picture that you see, white in color. That will be open this January, and we had to get the entire road that passes by. It was a county highway that was right next to us, and that we had to move that entire road to build this facility. And the road has now completely been moved. We were talking with Vicky earlier, and now we can actually travel through that. But that building will be ready, and there's 2 other buildings that are in the works, in the design phases, that are continuing to expand the capabilities that we currently have. Just a couple of quick pictures during the construction phases. This is before the road was actually moved. You can see the highway there between those 2 buildings. That's completely moved. Another nice thing you see also is you see PV panels on a couple of those buildings. I don't have a laser pointer here, but you can see various different technologies. And we have Dennis here that actually installed the PV panels. There's close to about 100 kilowatts of PV panels that we're using in the facility. The next building that we're building is an energy efficiency, deep energy savings, what we're calling a zero energy nano building, also mostly for education and training for a lot of the students that we have. So this sort of puts things in perspective. Again, a different view of it, and you can see that the road has actually moved to where there's these little hills at the bottom of this picture. And on the left, where you have the construction area, is where they're actually going to be building another building that's currently in the design phases. So this has all expanded very rapidly in a very short time period. And this relationship between us and industry partners is not focused and located only in the capital region. We are starting to expand our collaborations quite a bit. As you can see in this picture, we have taken over a center of excellence in Canandaigua, which is right outside of Rochester, New York. And we're building the same model with them. They have a MEMS facility that we're working with to partner and work with industry partners. We work with SUNY in Utica, the Information Technology University, SUNY IT in Utica. They have a campus, and we're building their nanotech capability. In Syracuse, we work with Lockheed Martin Electronics Park. You drive by 90, and you can see, it used to be the old GE Electronics Park for some of you if you've driven by there. That's a partnership with us and Lockheed Martin. And of course, there's the Global Foundries in Saratoga and IBM down in East Fishkill, and they're the manufacturing node. So the technology that we're developing at the college, in terms of the partnership we have, that serves as a pipeline for these companies to continue to innovate, to continue to develop new products and new processes that they can introduce into their manufacturing line moving forward. So that is how we're sustaining and developing what we call this nanotechnology hub in the region that's starting to spread not just across New York State, it's having a major impact in the industry as well. Over the last 12 to 15 years, the impact, if you just look at the impact of what has actually happened. Today, we work with roughly about 300 different industry partners, manufacturers, suppliers, integrated device manufacturers, people that make chips, people that design chips, semiconductor chips, people that design products for the chips. You know, the phones that you use, for example, the devices that you use are all partners with us located in our facility, working very closely with us. There have been altogether roughly about $14 billion so far in the last 12 years in terms of investment that has gone into this facility. A major part of that has come from industry. Today on site, we have 2,700 R&D jobs, mostly technologists. These are, you know, bachelor's, master's, PhD level. There's a lot of technicians. There's about 600, 700 operators, technicians that run the machines and operate the machines and maintain the place as well. That is expected to increase to about 3,500 by the end of next year when our new building is up and ready for people to move into that facility. Overall, if you look at the impact that we've had statewide, including the companies that we're actually partnered with in the state and outside, since 2001, over the last 12 years, we've had an impact of about 12,000 jobs, $1 billion worth of wages, and that is projected to increase significantly over time. So if you look at the partnerships that we have with the companies that we work with, I mean, these are the A companies, the B companies, and the C companies of the industry. The big guys, the IBMs of the world, the Global Foundries, Samsung, Toshiba, et cetera. On the bottom left-hand side, top right, you see Intel, TSMC, Sematech. Those are the chip manufacturers. And the top left are a lot of the equipment manufacturers, as well as the suppliers. So it's the entire supply chain that we actually work with. It's not just one or two companies that are making the product. What is important for any industry, and I'll sort of equate this in a second when I start talking about solar, when we move forward there, is building this ecosystem, if you will, not just from an installation base and deployment base, but also the entire supply, the suppliers, the people that are actually making the stuff, whether it's the panels, whether it's the racking systems, the wiring systems, the entire subset needs to be taken into account, and which is why we have been so successful in the nanotechnology space. Last fall, Andrew Cuomo, our governor, announced a major initiative to sort of step up the activities. New York is now, for some of you that may or may not know this, has been recognized by the industry as a global leader now in nanotechnology. There's no other region in the world that has the kind of momentum, infrastructure, resources, and capability. And this includes the workforce training that has actually been happening over the last 10, 12 years, which is a critical component of making sure that we can attract the kind of companies that we're talking about to this region. So there's a $4.8 billion initiative. This is brand new on top of the other investments that I already talked about. And for the first time, companies such as Intel and TSMC are starting to now locate facilities, resources, engineers, scientists, technicians in this region, because there's this critical mass that they need to be next to make this to be successful. A major part of that is also now starting to think about how a lot of this technology will include energy efficiency and other measures from a clean energy standpoint that start to make a difference in this industry as well specifically. So it's a significant investment that has been made overall, and that's continuing to be made. And you can see that initially New York State actually invested a significant amount of money when we first started to build the infrastructure. Out of the $14 billion that I talked about, $13 billion of that $14 billion has all come from industry. There's only a small fraction of it that actually was some seed money that was put up by New York State at that time. Now, what makes us successful? What is the key success ingredient? I wouldn't say there's any one silver bullet. There's a whole host of different things that have allowed us to be able to build this robust ecosystem, if you will, in the nanotechnology space. If you look at a traditional model of a typical university, what they tend to do is, you have university professors, faculty members that are working in their labs, doing research. They come up with these great ideas. They patent the ideas. They provide it to their tech transfer office. They apply for a patent. They get a patent, and then it gets licensed to industry. Industry becomes a partner or a customer where they actually give the patent over, license it, and get some revenues back from industry. We do things sort of backwards. We start talking to industry up front before we're developing specific technology, and that's why it makes our reason for being a little bit more relevant to industry partners. So we start to talk to industry up front, and we start to work with them on a continuum, if you will, short-term, medium-term, and long-term research and manufacturing type development. And while we're doing that, there's two other things that we do. We make sure that the workforce capabilities, the few people that we're actually training or educating, with with different degrees, that we're training them appropriately so that when industry hires them, they don't have to retrain them one more time. And that typically is what happened in the past. So our guys get picked up by industry very quickly, our students. And secondly, on the technology side, we want to make sure that technology gets handed over to them very quickly. So right up front, we negotiate agreements with industry partners related to transferring technology to them in terms of the technology that comes out of our activities, our collaborations with them, rather than doing it out after the fact. So industry is really happy with that process, and they don't have to renegotiate a license arrangement later on. Another key element, and this relates to the nanotechnology initiative too, from a workforce development standpoint, the National Science Foundation has said that within the next couple of years, 2 to 3 years, we are going to need about 2 million workers in this industry. This includes 20% of them that are roughly about scientists. 80% need to be highly skilled engineers, technicians, business leaders, economists, etc. So very early on, and going back when we initially created the college back in 2004, we recognized this already. And we said, we need to create this college and at the same time work with industry to develop the talent that industry is going to need, not just from developing commercial technology standpoint, but making sure that the workforce is there for industry to actually happen. And so we really need to start training these guys now. We're already at that level. At a panel discussion yesterday, I mentioned that we have a challenge of attracting students not just to the clean tech community, but also to science and technology and engineering and management and math specifically. There's not many people that are getting trained in those areas. So we're starting to reach out in those areas, in the high school, in the middle school, and the lower school as well, and we try to bring these students to our facility and create programs with a lot of the local schools and communities to actually start to do programs with them in that space. So let me tell you a few things about Nano. Now, I'm going to shift my discussion away from the actual college, talk a little bit about Nano, but before I do that, how do we define Nano? And people sometimes ask us, what is this? Is it about really tiny things that you guys are working on? If you look at it, yes, there's nanoscience, there's nanoengineering, and nanoeconomics. And between the three of them, we believe it covers, there's one more, there's Nano Bioscience, which covers the healthcare, medical side of things too. Between these four areas, I think this covers the gamut of all the technology that exists in the world today from our viewpoint, of course. If you look at nanoscience, the fundamental understanding, everything is made up of atoms and molecules. And if you can start to understand the effect of how these atoms and molecules can come together and be able to manipulate them, because there have been proof of when you get down to those levels and when you start to build things up from the bottom up, you start to get completely different characteristics and functionality and properties of materials. The way you actually design them is much easier and better if you can do it that way. The engineering part is still lacking. We still don't know how to actually do it in a very, from an engineering standpoint, but that is coming. So the engineering is actually applying the knowledge that we've learned on the science side and be able to apply it and build devices and things that were not possible. And I'll give you examples of that as we go forward. And then if you look at the nanoeconomic side, it's basically the business of nanotechnology. It's understanding, how you do the making sure the collaborations work, making sure the economic, the demographics, and all of that. So it's basically if you look at economics just by itself, it's still quite different from our standpoint. It's very different from actually looking at it from really a technology perspective. So because of this, as I mentioned, we have actually created a bachelor. So you can actually come to our college, you can apply to it, and get a bachelor's degree in nanoscience or in nanoengineering, or a master's degree or a PhD degree. We started back in 2004 is when the first college started, but we had 10 graduate students from a prior program in physics and chemistry that were there already that transferred over. But today, as I mentioned, we have about 250 graduate and undergraduate students enrolled in the college. We have some very unique classes, and so the same description I was telling you about earlier, where you teach a scientist, a chemist, chemistry, you teach a biologist, biology, et cetera, what we try to do is we try to mix it up. So our students, we have foundation classes in chemistry and biology, and I'm not talking about just the graduate level in the first couple of years. I'm talking about follow-on years as well. I'm also talking about in graduate school, where we have these foundation classes where we bring everybody together and mix up their knowledge of chemistry, physics, basic chemistry, physics, math, biology, et cetera, in a way that they wouldn't learn otherwise in a traditional siloed department. Now, based on our model, there's others. I've mentioned just a few, but Stanford has also started to offer now a nano degree at a graduate level as well as an undergraduate level, in addition to the ones over here. So this is starting to take hold, and this is where truly the interdisciplinary aspect of the science and engineering starts to play a major role in what we're trying to do moving forward. So in addition to just the degrees for higher education, we also work very closely with a lot of the community colleges, local community colleges. I mentioned already the high school programs and undergraduate internships that we provide. There's a Workforce Development Institute that we have that's organized by SEMI. It's the Equipment Manufacturing Organization. We have programs with equipment suppliers to train people to actually run the equipment, operate them, maintain them as well. And then there's also a skilled trade program where in this industry, it's very specific as it relates to training even an electrician or a plumber in terms of how to actually set up a clean room, for example, or to actually hook up a tool in the clean room. I mean, the type of protocol and the requirements that are needed are very unique and very different from any other industry. So those are a lot of the training that has to also happen as we move forward. So let me shift a little bit, talk briefly about nanotechnology and explain to you what nanotechnology is, other than the high-level descriptors that I gave you related to science and engineering. If you look at this chart, I'm going to basically focus you on the top side of it primarily. Now, if you look at the size of a soccer ball, a little less than, it's about 22 centimeters in diameter, somewhere between the 1 meter mark and the 100 centimeters or 10 millimeter type numbers. Now this whole range goes basically, there's 10 orders of magnitude. You go from 1 nanometer to about a meter. 10 to the 9 is the number that you actually look at. And there's various things in between. There's another ball type shaped structure that you see at the top right hand side. That's a buckyball or C60 that was discovered several years ago. And that is the size of a little less than a nanometer. So that sort of gives you the whole size range of what we're actually talking about. In between, you have red blood cells. You have the human hair, which is roughly about 100 microns in size. 100 microns is 100,000 nanometers. So you have to actually take that, picture that, each hair follicle that you have, and if you slice it up 100,000 times, you get to about a nanometer. The structures, the device structures, you see in the bottom right-hand side where you see the IBM logo there, that is each of those atoms are sub-nanometer size. As it says over there, each letter that you see is about 5 nanometers in size from top to bottom, and that was actually created by actually moving atoms around. This was created by some IBM researchers about 12 years ago. So you can see how a logo is created by just moving atoms around at the 5 nanometer level. A DNA strand is roughly about 2 nanometers wide, and a lot of the structures that you see today in a semiconductor chip or in what you have in your phone, for example, are structures that are typically in the 10 and 20 nanometer type range and going smaller and smaller in terms of packing more density into these chips. So this sort of puts things in perspective. Now, one of the sayings that we have at the college that the smaller you go in size, the more expensive our research gets in terms of orders of magnitude, as well as the types of equipment that you need to be able to do the types of things that you need to do. But remember, as I said, if you go down to those lower size levels and can control atoms at those levels, and if you can build small things, if you can build a robot or a little motor, people have done that. They've actually built a motor taking atoms together and at the research scale, not at the manufacturing scale, and you can actually run a little motor at that scale. And the properties and capabilities that you can get from that kind of a motor are very, very, very different from what you would from a typically, motor that's wound with copper wire, as an example. So very, very different phenomena start to take place at those levels. That is why this is emerging as a new science and a new technology that is going to change the way we look at how technology gets implemented. So, and this is not just us. The entire there's a lot of activities around the world, in Europe and in Asia, that are focused on nanotechnology-related developments. When people talk about nanotechnology, they sometimes think, is that an industry, or is that a product? And when you start to think about it that way, you're not thinking about it correctly from our perspective. For us, it is really a general purpose technology platform. It's, as I said, it's a new field. It's like saying that there's a new field of chemistry coming around the corner. And that is nanotechnology. So it's a brand new field that is going to actually impact all of the other disciplines that we're talking about. It's going to have an impact on clean energy. It's going to have an impact on biomedical engineering. It's going to have an impact on semiconductor chips, et cetera, et cetera. So you're going to start to see more of that happening in the next several years. And just in 2005, this is some old data from Lux Research and some new data in the chart below. But if you look at all the goods that were manufactured using nanotechnology in 2005, it's already a $50 billion revenue type number. And you look at it in terms of the next 2 to 3 years, the products that are going to incorporate nanotechnology is going to exceed $3 trillion in terms of capabilities. I mean, the way this is looked at is, for example, if you're buying a phone and it has a chip in there that has nanotechnology-related elements in there, this is sort of the revenue that you get from that entire phone, of course. But it does put into perspective all the different things that get impacted by nanotechnology and how important it is in our everyday life moving forward. Let me explain the two different approaches of nanotechnology and how things are actually made before I get into some applications that puts things in perspective for you. The traditional way of basically taking a metal or a material and the blacksmithy approach of beating it and getting it down to a size and shape that you want to use and making a chair out of it or making a sort of a steel bar out of it is what we consider a top-down approach. Now, to make small sizes in the semiconductor world, you use something like lithography, electronic, and that makes you get down to smaller sizes. You can actually get down, today's technology can get you down to at least 50 nanometers in size. This is the size I was describing earlier. It's several sizes of those buckyballs, for example. I mean, if you take 50 of them, you can get to the size of the devices that we're trying to create. Eventually, we're talking about creating quantum structures. Quantum structures are sub-nanometer type structures that you can actually create devices out of. And you can do it from a top-down type approach. Everything from thin film deposition techniques, chemical approaches are how you can actually use this. Then there's a bottom-up approach that also I was describing earlier, where those IBM logos were created, where you started with those atoms, and you're trying to take these atoms and put them together and create a device or create this motor that I talked about. And that's also called self-assembly. And this approach is considered to be more of a revolutionary approach. From the standpoint that our current manufacturing approaches don't use this approach, but if you can use this in combination with the top-down approach that I talked about earlier, that's when you're going to see big changes in the way things are actually made moving forward. So that's something to just keep in mind, the top-down versus the bottom-up approach of trying to make products in the nanotechnology space. And it has all kinds of consequences. Inorganic materials, everything from metals, ceramic materials, can be molded using nanotechnology-related techniques, and so can organic-based materials and DNA molecules, proteins, things like that that make up a body or a medical type, whether it's a device, can also be built from nanotechnology-related approaches. So as you can see, these have implications across the board. I already mentioned that it cross-cuts the sciences. I mean, because when you start to talk about a brand new field, especially not knowing what nanotechnology or how it could actually affect our everyday lives. I mean, there is concern in the community that, you know, if you start to breathe these nanoparticles, what happens to you, right? I mean, that starts to become a problem. And so there's a lot of ethics and public policy and law-related issues that have started to come into play as it relates to nanotechnology. So it's a huge field in itself. I mean, it takes disciplines from all the different categories that we just talked about, the life sciences, the material sciences, the electrical engineering, the information technology. All of these get impacted when you start to think about nanotechnology and the implications it actually has. So the implications, the societal implications are huge. The way you got to look at this is it allows you a very basic understanding of how atoms and molecules come together and provide you with some really unique properties that you wouldn't get otherwise in bulk materials that we talked about. You can have a tremendous amount of improvement in healthcare. You know, you can improve. I mean, we have research and technology development initiatives going on at our college related to improved drug delivery, for example, using nanotechnology-related approach, and I'll sort of show that in a second. There's also new drugs that can be found using nanotechnology and can have a huge impact. Sustainability is a huge element. How do you actually improve on agriculture and food type production, whether it's energy, water, environment can have a huge effect. I mean, you know, water as we know it is going to be one of those big challenges in the next century for sure for the planet Earth. I mean, after energy, of course, clean energy is one of the things that we're trying to use to benefit, but water is something that we're going to have to be worrying about soon too. And then there's direct economic development opportunities that nanotechnology brings because it has such a broad impact across all the industries that I talked about. So let's just talk about some of the products that we're aware of that we produce today and use on a regular basis. I mean, you could put it on a chart that describes whether it has a huge impact in terms of dollar value or an impact as far as nanotechnology is concerned. So what you can see from this is, I mean, the four industries where you can really have a big impact with nanotechnology are energy, healthcare, computers, and telecommunications. Okay, so there's other industries that it also has a big impact on, everything from transportation to chemicals, petroleum, glass, metal, plastics, etc. It does have an impact. I'm not going to talk too much about those. I'll just briefly touch upon the four key areas that are listed above there and give you examples of what they ought to be. So you can use nanotechnology in a variety of different ways. You can just use them as nanomaterials themselves, and I'll give you examples of how nanomaterials can be used. I mean, you know, you can form composites. You can use them. In fact, the cars, for example, the body of some cars from Japan, Toyota primarily, incorporates nanotechnology-related composites in the fiberglass of the body, so they make them lightweight and stronger and resistant to impact. Nanomaterials are also used, for example, in fabric. There's examples of that. There's sensing and measurement capabilities that nanotechnology can provide that was not possible before. You can put sensors on the size of a grain of rice and basically distribute it all over this room, for example. You wouldn't even know where it exists. And it can sense everything from, you know, what molecules are there up in the air to, you know, whether there's some hazardous substances there or whether there's somebody breathing or whether there's somebody moving in the room, and you wouldn't even know about it. And maybe a camera inside of that grain of rice that can also see what's actually happening. That technology is here already. It already exists. There's electronics, there's communications, energy, the biomedical area, as well as aerospace and defense. And I'll talk about that in some of these, for examples. So if you look at nanomaterials in general, nanomaterials can be used as catalysts. Catalysts are substances that enhance chemical reactions. To have a much better catalyst, the key property that you need is it needs to have large surface area. So if you have something that has very large surface area, you can have much better reactions, for example, for catalyst type property. And one of the key ways to get to larger surface area is to go down to as small a size as possible, and that gives you the largest surface area that you can. So catalysts are already being used. This technology is already implemented. I mean, from everything from refineries that use catalysts for chemical reactions, rocket propellants, explosives, conversion of coal to fuels, for example. There's different types of coatings that use nanotechnology. And these can be both organic or inorganic, epoxies, paints, durable type materials, window glass plates, suntan lotion, believe it or not. There's particles in some of the suntan lotion that gives you the different ranges of the capabilities, the tanning capabilities that you have, the protection that you get. Is basically a consequence of the amount of nanoparticles that is put in the lotions. Don't worry, those are pretty safe from what I understand. I mean, I'm not a medical doctor, but I understand that those tend to be pretty safe. Composites, I talked about cars, automobiles already introducing composites that have nanotechnology related elements implemented in them already. If you look at sensing and measurement techniques, gas sensors, leak detection, there's things like hydrogen sensors, gas, and I'm talking about even gasoline, petroleum-based sensors. If something leaks, you can have these small particles that are basically distributed all over the place. Environmental monitoring as well as industrial control sensors. These already exist. They are applied in a variety of different industries today already. There's biological detection. You can do things like obviously identifying specific genes that are located in the body, and all of that requires sensors. And if you can turn them around at a much quicker pace from a speed of detection standpoint, that's what helps. And nanotechnology plays a big role in that. The spectroscopy as well. Electronic side, we've already talked about this. Everything from the computer processors themselves, the chips. The reason why we're trying to go smaller and smaller and smaller in size is what we call Moore's law. It's sort of one reason is we try to get the consumer to buy a new computer every second year, right? That's one of the reasons. But what is actually happening is because the technology is advancing so rapidly, every 2 years the speed of a computer, as we know, doubles. And that happens because we're putting more and more of these chips or transistors on a single chip. And when you do that, the amount of signals that you can get and how quickly they actually work increases substantially in terms of its speed. So that is why we're trying to make these smaller, and the more you put in there, the better off they are. And we're also, it's also related to the amount of area that you have. So now there's techniques that people are using. It's like Manhattan. You have a limited amount of space. So instead of actually putting more buildings in that limited space across that room, the only way you can do it is to go up. And these days now, the computer chips that are being made are transistors that are built one on top of the other too, and that's how you can get additional speed that's accelerated at different paces. Display technology, flat panel displays, organic LEDs, all of this technology uses nanotechnology, right? So LEDs that we have today, the technique that you use to make the PN junctions in an LED is nanotechnology. The process that is used to make that is nanotechnology, including field emission and flat panel displays. And storage, you can imagine how much information now you can store in your computer. It used to be back in my time when I was in school, we were happy when we had a 512 KB memory card on your computer that you would have, and it would be these floppy disks that you would actually put into your computer and save the information. Today you can go up to gigabytes of information, right? And that's all because nanotechnology has allowed us to go smaller and smaller in size and store more information in these devices as quickly as possible. Biomedical, I talked about how nanotechnology has a big influence on biomedical applications. Drug discovery, trying to come up with new drugs. How do you deliver the drugs is important. Diagnostics is very important too. So everything from MRI contrast agents, sensors, detection labeling are areas that nanotechnology has a big impact on. Implants in surgery, Electronics that can be implanted also in the body are key things that are looked at. And again, a lot of this technology already exists. It's a matter of doing enough studies on how it actually has an effect on, for example, the human body or on the life before they start to get implemented. I mean, the other technologies where it's starting to become ubiquitous is you have computers in your phone. That's the best example of nanotechnology in action. The chips in your phones. Another example that's typically given is if you have a smartphone, if you have, for example, either an iPhone or a Droid phone or any one of those phones, right? The amount of computing power that you have in one of those phones today that's in your pocket is the same amount of computing power that they had, back in the 60s when the Apollo mission was, the amount of computing power they had in that mission going to moon. So we usually tell all the folks, especially the kids that we deal with, if you have one of those phones, you can go to the moon. I mean, it's sometimes as simple as that. That computing power makes a difference. It makes a huge difference. It tells you how much what you can or what you cannot really do with it. Energy. I'm going to go a little bit more detailed in terms of the impact on energy. It has a huge impact. Nanotechnology has a huge impact on energy, and that's why we at the college have been working in this space for the last 15 years now already. So clean, less expensive sources of energy. Renewable technology, solar cells and fuel cells have a huge impact. Nanotechnology has a huge impact on that. I talked briefly about solid-state lighting. Power electronics are basically semiconductor devices, and they're getting better and faster and easier to work with, for example. There's storage technologies, batteries and capacitors that are now starting to be deployed on a much larger scale. And then eventually there's the hydrogen economy, which is the alternate fuel technology, which will also happen over time and requires a lot of advancements in nanotechnology. So nanotechnology, in a way, is here to stay. It's going to happen, and it's important to understand also the timing. I mean, so the way you have to look at it is it's a continuum again, as I said before, too. This is not something that happens overnight. You're going to start to see, in next 2 days or next 5 days, you're going to start to see a major impact. If you look at it, provide some perspective, it's only now that we have been, and the nanotechnology is really an evolution over a period of time, right? I mean, and the reason nanotechnology has come about is because 20 years ago, 50 years ago, we did not know about nanotechnology because we did not have the tools to measure or make things at that level. Today we do. 50 years ago, we could make things maybe at the micron or the millimeter level. So we would make products, we would make things, we would make devices, all the types of products that we knew and would understand was done at that level. Today there's new devices, these characterization analytical tools that are there that allow us to do things at the nano level. That's how nanotechnology has evolved and come up to a level. So in the short term, being able to make some simple, straightforward devices at the nano level are going to be pretty common in the next 5 years or so. In the next 5 to 15 years, I'm predicting that you're going to be actually doing a lot of the self-assembly that I talked about and directed assembly, building a lot of these devices from the ground up that we talked about. Again, not everything under the sun, not every little product, not your whole phone, for example. There's going to be key components that actually use nanotechnology-related approaches and simple things that will happen. In the much longer term, nanotechnology is definitely going to have a much bigger impact. I mean, you're going to be able to manufacture things with absolutely green concepts, with zero waste and not using solvents and things like that as an example, because you can start to create these things from the ground up. So let me talk a little bit about now how nanotechnology as a whole and how you've understood this. Now, remember, there's going to be a quiz at the end of this, right? I'm going to be giving you questions. So let me talk a little bit about how we at the Nano College are applying nanotechnology in the clean energy space. And I'll talk about this briefly, and then we can move on to actually solar. So I talked about the Energy and Environmental Technology Center that we've had at the college for the last 15 years. We work very closely with NYSERDA, as Vicky has indicated. What we're doing is, the education component is critical. I mean, telling people about nanotechnology and how it impacts our daily lives has become fairly routine for us, and people are starting to get it. So the same in the energy space. So it's not just the technology that we're trying to develop, it's also making sure that we provide the right education, outreach, training, workforce development, and also tech transfer and business commercialization that I talked about on the nano space. So we're trying to do that in the energy space in a big way as well. We're focused in 3 main areas because these are the areas that nanotechnology has quite a big amount of impact on, and I sort of divided it up into 3 key areas. In the short term, we have things like smart grid, energy efficiency, and I put that in the short term category primarily because this is very industry driven. Technology already exists for implementing a lot of energy efficiency type capabilities, everything from green buildings to monitoring control systems, power electronics, power quality, et cetera, are things that can actually happen right away. And so we play in that space by doing demonstrations, working with our companies, using a lot of the technology that are applied in this field and actually improving it at an incremental type level. The second category is disruptive technology. And I put solar in the disruptive technology space because there are some aspects of it that are still technology driven. And I believe it's sort of at a tipping point where the moment we start to hit specific targets in a cost perspective, and I'll talk about that also a little bit later on more in detail, but solar is going to take off from an industrial perspective. It's already been growing worldwide at a fairly large rate, and this is going to be an industry that is going to be there for the long term for all of us to try and benefit on. And the longer term category is what I call energy storage, primarily for large scale applications. I'm talking about for grid and for building scale applications, batteries or capacitors or fuel cells. You'll find batteries on your smartphone, for example, or in your computer. Very viable there. That technology makes a lot of sense over there. And there, you're buying it for convenience. You're not buying it because it makes a lot of sense from a return on investment perspective. But when you start to compete with generation resources, energy storage has a long way to go. It still has a lot of technology development and cost reductions and also durability type enhancements that need to happen. So I sort of put that in the long-term perspective, and I say that policy is going to drive a lot of the technology development in that space as we move forward. And the way we position ourselves, as I mentioned to you before, we play in the space of life sciences and materials nanotechnology, and we do have a lot of capability in computers and information technology at our place. So we sort of use that knowledge and capability and try and penetrate into various different areas of clean tech, whether it's photovoltaics or energy storage or fuel cells or biomass or in fact smart grid and buildings as well. So we start to have this penetration effect. And the way we do that is really partnerships. So we bring our strength and capability to the table together with industry partners and others that can add significant amount of value, whether it's a utility, whether it's an industry that's providing a service, or it's an industry that's making a product. We don't necessarily step on the toes of our industry partners, but we want to make sure that we are there providing them with their needs, whether it's tech transfer, whether it's the right workforce, or whether it's any other thing that they actually need to help them in all of these different spaces moving forward. So again, just a repeat of some of the products that we're actually developing using nanotechnology on the photovoltaic side, power electronic side, superconductivity is another area we get involved with. Thermoelectric devices are pretty neat. They use them in the computer industry quite a bit. Trying to build large-scale devices are still a challenge, and that's what we're working with some of our industry partners. Capacitors, ultracapacitors are a new emerging technology, especially lithium-ion-based capacitors that are right in between batteries and lithium-ion batteries and the traditional EDLCs, the electrical double-layer capacitors. They have very high power density as well as energy density, and so they're a huge benefit, and we're working in that space. We also work on fuel cells, PEM, as well as hydrogen sensors in our lab. So, where does nanotechnology, so when I talk about fuel cells, where does nanotechnology play in fuel cells? Just to put things in perspective, right? The heart of a fuel cell is basically a membrane with some electrode assemblies and basically you have an electrochemical reaction taking place at those interfaces. At those interfaces are these nanoparticles or catalysts or these electrodes where a lot of these reactions take place. If we can build that electrode from the ground up, we can make a fuel cell 100% efficient if we could do it and engineer it the way we actually want it to. Today, it's roughly about 40%, maybe 50% efficient, maybe 60% efficient if you try to recover some heat out of it. But imagine trying to build that thing from the ground up and making it 99.9% efficient, if not 100% efficient. So that's the kind of impact that nanotechnology can have on this space. So the areas that we work on are optimizing some of the processes, trying to reduce the cost. This uses platinum. Platinum is a very expensive metal. Give you another real live example. I mean, if you take platinum particles, which is the catalyst, and I talked about the surface area of the platinum that's actually used in the reaction. So if you have a ball of platinum, basically the stuff that's inside of the ball, the platinum metal that's inside the ball, is not doing you any good. But you still have to carry that weight, and it becomes expensive. So one of the approaches that we've come up with, we work closely with Brookhaven National Lab down in Long Island, and we've developed a way where the inside core is basically a cheap metal, such as nickel, and the outside is platinum. So we're using just a mono layer, an atomic layer of platinum on top of that nickel surface. And can you imagine the amount of cost savings you get by doing that? That's nanotechnology at its best, if you will, and trying to get the cost reductions that you can get out of it. So again, just a quick example to put things in perspective in terms of what it can actually do for you. And it's not just making the solar cell better. You can make these products pretty small too. So here's an example. In Japan, they actually produced a very small fuel cell that produces several watts of power at that scale. It's pretty amazing that using the type of nanotechnology-related approaches that we have available to us, you can actually make that happen. Solar cell, same thing. The key to solar cell devices is, I mean, these things tend to be only 10, 15, 20% efficient today. And the reason why it's only 10, 15, 20% efficient is because these things are not engineered from the ground up. Again, imagine if you could actually make a solar cell from the ground up. I mean, again, I'm thinking about now giving you a vision of something that could happen 15, 20 years from now. But eventually, that can happen. You can get a solar cell that's 40, 50% efficient. In fact, there's a company that we're currently working with that has produced, using nanotechnology-related approaches, a solar cell that's close to 30% efficient at a fairly large scale, not just a teeny-weeny sample. They've actually produced a large module that's close to 30% efficient too, using nanotechnology-related approaches. Again, reducing the amount of materials content in a solar cell to get the cost down, improving the resistive losses, maximizing the absorption of light that the solar cell actually sees. I mean, all the action happens at the electron-hole interfaces, and these are all nanotechnology-related developments. If you can make it perfect, if you can make the crystal of the solar cell perfect the way it should be for it to absorb the light and transfer the light into electrical signals, you can make something that's fairly efficient moving forward. Here's some examples of some more futuristic kind of technology using organic-based plastic materials. Imagine your shopping bag that you get from your grocery store. You can convert that, you dope it just the right way, you can make it into a solar cell. There's actually a company that was actually doing this. They've not been successful in it, but there's still a lot of technology and a lot of durability-related issues that they need to benefit from. But these are all technologies that are going to be coming down the pike pretty soon. Let me shift a little bit and talk about the solar PV opportunity. Before I do that, we all know that energy is an important part of our daily lives, economic development, et cetera, et cetera. I mean, if we didn't have energy, we wouldn't be sitting here talking and listening to this talk for sure, but we wouldn't be doing a lot of other things too. I like to use this chart. This is one from a good colleague of mine, Richard Perez, over at the University of Albany. And the way he looks at it is think about how much energy we use today. The world uses, this is actually 2009, about 16 terawatts of energy. If you look at it, well, maybe 2050, how much is it going to be? It's probably going to double. Question is, do we have enough of the reserves, oil reserves or petroleum reserves or coal reserves, to be able to provide that? Actually, we do. So total coal reserves for coal out to 2050, we have plenty of coal that will last us, looks like, at least till 2100 at least, too. Petroleum also, there's plenty. There's 240 equivalent gallons of that, equivalent amounts from a terawatts perspective. Same thing with natural gas, same thing with uranium for nuclear. When you start to look at renewable type resources that are available in the world, wind is not as much as some of these other ones, right? I mean, there is plenty of wind, but it's not as much as these other ones. Waves, ocean thermal energy is one example and this is another example of renewable. Biomass, that's the total amount of biomass that could be available for everybody to use. Hydro resources, about that much on an annual basis. Now, one thing to remember is these are all on an annual basis relative to what the world is going to use on an annual basis as well. These are the total reserves that are actually available. And tides. The one thing that people really don't think about from a big perspective, well, we all do because we are all in the clean energy space. I know everybody in this room, I'm hoping, is thinking about solar because on an annual basis, there's 23,000 terawatts worth of solar that comes to us on a regular basis. The question is, why aren't we focusing in on using that resource in a big way? And the reason is, for the past 200 years, mankind doesn't think logically, right? They think about what's the easiest thing to do. Let's look down and drill for oil and drill for coal. So again, just a simple thinking process that we sort of started this whole process backwards. We should have originally looked up into the sun and said that's where we should really be getting our energy from. Let's look at the solar energy today. Today, the way I describe it, worldwide, there's about 60 gigawatts of solar installed worldwide. On average, it costs roughly about $4 a watt to install. There's significant overcapacity. The whole business, the market is completely fragmented. There's everybody fighting with everybody else. Nobody's talking to anybody else. There's no standardizations, very little standardization. There's very little benchmarking that goes on in terms of best of breed kind of efficiencies. A lot of the applications tend to be rooftop generation. There are some big power plants, not many, a few power plant applications that are in the works. In the short term, I'm predicting this is going to go on for the next 3 to 5 years. Survival of the fittest in terms of all of the suppliers and all of the players, even the installers and everybody else. It's going to be survival of the fittest. If you can manage and if you have the strength and the wherewithal to hang on there for a long time period, you're going to start to see more off-grid applications. And you'll see why I say that. And then there's the grid tide is also going to continue to grow. In the longer term, we're predicting that you will see, and when I say longer term, this is not 50 years out. I'm talking about 10 years out, 10 to 15 years out. You're going to see close to 400 to 600 gigawatts of solar installed. Installation costs that come down are going to be at the dollar, less than $1 per watt. This is not just buying a module. This is the overall installation cost. Industry is going to be expanding significantly. There's going to be global manufacturers and suppliers supplying the entire industry. And it's going to be for very specific applications. Solar is going to find its niche in peak capacity and demand response type applications. It's not going to compete with the coal and the natural gas. That's not where solar should be really playing. It should be meeting some real key applications in certain areas that we're talking about. So that is going to happen. This is a matter of who survives and who's going to capture and take care of that market opportunity that we're talking about. The reason I say that is worldwide, there are still 2 billion people without any access to electricity, okay? And rather than build large power plants, gigawatt scale nuclear plants or power plants, or whether it's a gas-fired or a coal-fired power plants, you're going to start to see things like solar panels be implemented at the village level in Africa, in Asia, in a lot of the developing countries, South America, et cetera. There, it's going to be a lot cheaper to do this. It's cheaper to do this today than it is to build a large plant and string transmission lines across the entire region. It's the same basic concept. The reason why some of these countries have leapfrogged the developed world when it has come to the telecommunications, the cell phone type marketplace. I mean, they never had the infrastructure for landlines. What they did was they went and invested heavily in base stations. And the technology that they have in some of these developing countries for cell phones is far superior to what we have here today. Okay, they've got 4G already in a lot of these countries. And the same kind of technology leapfrogging is going to happen in some of these countries moving forward. In fact, there's a McKinsey report out that talks about where the markets are going to be. The US is still going to be a fairly large market area for solar cells. So is Europe, and you can look at Asia. Everything from peak capacity to isolated grids. The number talks about gigawatts. I mean, this is going out to 2020. And the gigawatts of solar installations that are going to happen in some of these regions around the world. So this is the reason why I'm also saying that this is going to be a huge growing market moving over. But what do we do in the US instead, right? I mean, you look at this. I'll let you just quickly glance through this without me reading the details over there. What does this tell you? This tells you in the developed world, it's the incumbents that are trying to control where everybody gets their power from, right? So unless we try to change this kind of mentality and thinking, it becomes hard for us to try and find the right opportunity for the clean energy technologies that we're talking about. But there's going to be new applications for PV. The applications are going to be from everything from building integrated. People have talked about building integrated for the last 20 or so years. I'm predicting that in the next 10 years, you're going to see a lot more building integrated because the kind of technologies that are coming online, sort of along the lines of the nanotechnology related developments that I talked about, flexible PV, et cetera, are starting to make these new approaches a lot more feasible moving forward. Because of that, you're going to start to have these venture capitalists that are trying to seize the opportunity. This is actually not such a good thing. I mean, I show this in a facetious way. Yes, they're trying to capitalize on the opportunity. But what tends to happen is this big boom and bust cycle that typically happens, right? When everybody gets all greedy about trying to benefit from this in a big way. It happened in the telecommunication industry. It happened in the IT industry. I mean, it's basically happened in the real estate industry, everywhere. So this is what today the US is facing. I mean, we hear about the Solyndras of the world and all these other companies that are going under because they were all funded primarily by bad decisions that VCs also made. It wasn't just the government, it was the VCs that were backing them and sort of trying to get additional funding out of it. So in a way, it's a good thing, but from a whole perspective, it's not such a good thing. So that is why this brings me to what we're trying to do at the college is we've created what we call the US Photovoltaic Manufacturing Consortium. And this is to address exactly this problem. If you look at this chart here, the black line was the US market share of PV that was produced worldwide. In 1995, we produced about half of the PV. Back in 2010, that number is 7% of all of the PV that's produced worldwide. You look at the growth in the marketplace in terms of, on the right-hand side, the PV module shipments. I mean, this is a multi-billion, tens of billions of dollars industry today. Who's getting the benefit of this? Not the countries, not the people, not the workforce in the US. Right? So this has to change. And this is why, Secretary Chu had announced about a year and a half, 2 years, or close to 2 years ago, the Sunshot program. And he equated that to the moonshot that President Kennedy had introduced, when we were trying to fight the Cold War with the Russians at that time. So the same thing here. We're trying to address this curve, the curve that's going down on the PV side. So what they did was they created this PV Manufacturing Consortium, and it's built on the same model that I talked about that we've done in the nanotechnology space, where we've brought these supplier companies, this entire supply chain, if you will, together to be able to manufacture, co-develop product, transfer the product to manufacturing, And the investment is pretty significant as a starting point. I mean, it's still not a $14 billion investment. It has to get there at some level to create the critical mass and the robustness of the suppliers, the networks, the infrastructure, and things like that for this to happen. We're focused on next generation technologies, the more innovative kind of things where we're going to continue to make new types of innovations. We have several companies that are already engaged. And you can see we're not focused on the basic R&D, which typical universities tend to be focused on. We're focused on high volume manufacturing, transferring the technology to manufacturers and investors, and the manufacturers that are actually making the product, right? So it's absolutely critical that these guys have access to brand new technologies every 2 years. Every 3 years, the costs are coming down so quickly in solar that if you build a plant today, in 3 years, that plant is going to be obsolete. And you're either going to go belly up, or you have to have that next generation technology to produce the next generation product. That's what we're looking at providing to our partners. We have a whole host of companies that have signed up. NYSERDA is also, again, a major partner with us on this initiative. And we have several companies, manufacturers, suppliers, research partners, equipment manufacturers, et cetera, that are part of it. Thin film PV is one of the areas we're focusing in on. Silicon is also what we're focusing in on and making it better using nanotechnology-related innovations. I'm going to skip through some of this. There's still some challenges that we definitely need to overcome. But one of the key things, as I mentioned, there are no standards. There are no roadmaps. There are no places where you can go to show proof of concept or proof of feasibility for the technology that you actually have to develop. So that's what we're providing. And last but not the least, you see the bottommost bullet over there. Workforce training is a critical component of this. The reason why we were successful in the nanotechnology space was we all put our heads together, the entire community in this region, including the community colleges, the K-12 programs, the universities, for to provide the technical talent to grow the high-tech industry in the capital region over here. And so we're looking at doing the same thing, establishing the infrastructure and the capabilities to train some of these people at the manufacturing scale as well. Some of the manufacturing tools that we're bringing online, you see the size of the tools. The one on the top right, you can see the person standing right next to it. These are actual full-scale manufacturing tools. And our people, we train our workforce on these tools. So we get them to actually work on these tools hands-on and get to learn. And so when industry is looking at hiring them, they're right there available for them to. So these tools will be, this line is going to be up and running in the next about 6 months to 9 months. And it's actually located in Saratoga region, not far from here, about 20 minutes north of here. We all know about costs. Costs need to come down significantly. It's not just the module costs, it's also the balance of system costs. And it's installation, it's financing, it's customer acquisition. And we need to train our people to start to improve and reduce those costs. Permitting, interconnection issues for solar is also important. And we're addressing those as well. So as part of the PVMC program, everything from permitting, interconnection, inspecting, the wiring pieces, the racks, standardization of a lot of these things is a key component. And so that's what we're trying to make sure that we do with the partners that we have. We have the whole, basically the supply chain that's helping us to get to that level. Ultimately, our goal is jobs, green manufacturing jobs, of course. This is the buzzword, not just for us, for everybody in terms of the politicians, and I'm sure for you as well in this room. So if we're successful, like we are saying we're going to be successful on the PVMC side, like we are on the nanotechnology side, we're looking at several hundreds of jobs already with the consortium that we have. But once we're also looking at hopefully attracting major manufacturers to the region that'll manufacture modules and cells. And if we can produce so just think about this. If some of you are from the region, if you can in your mind see the Global Foundries facility that produces computer chips today, that uses technology from the nanotechnology related innovations that they implement on the manufacturing scale. That scale of a manufacturing facility for PV is what is going to get us to that level of success in terms of production, manufacturing, and building that entire cycle of, in fact, in using it here and installing it here. And we're talking about tens of thousands of jobs from a successful sort of opportunity standpoint. So as part of the DOE program, our goals are very well aligned with the Department of Energy. We're trying to achieve the dollar per watt goal, R&D commercialization. So we're not just doing research of nanotechnology for the sake of it. We want to make sure that we commercialize it. US competitiveness is a key element of it. The last thing I like to see is our dependence on going from buying foreign oil from the Mideast countries to buying solar panels from China. I hope nobody else here in this room would like to see that either. I know there's a lot of debate about that from a cost perspective, but that's again not, it's going from the frying pan into the fire if you ask me. So US competitiveness and US jobs are critical to make this happen. And so building collaborative programs is the way you get away from the individual companies that are actually failing. Getting these companies to come together is really the way to do it. Partnerships, it's all about partnerships, partnerships, partnerships. So I'll end with this slide, and I know that we are short of time. I think our successful co-location model, I can, as I said earlier when I started, I can keep going about the benefits. What do you expect? All of us are educators here. Professors standing up on stage can talk for hours. So